So thank you very much to the organizer for giving me this opportunity to present my work. My name is José Morán. I am PhD student at CORIA laboratory in France under the supervision of Jérôme Dion. So today I want to tell you about the effect of soot maturity on the aggregation kinetics and morphology from a numerical study. So first of all, a little of motivation. It is typically said in the literature that particles below 20 nanometer, they exhibit a high size-dependent properties, such as, for example, catalytic effect or melting point. We have observed before in experiments, for example, in a diffusion flame, here a Goulder flame, we have observed different levels of soot maturity within the flame. And for example, we have observed in the wings that the maturity level is achieved faster than in the center line. Soot maturity might be a criteria for particle design. For example, here in a recent review from Baldelli et al., they review different modes for doing coating with these soot particles, and the different chemical and surface rugosity characteristics can lead to hydrophobic or hydrophilic applications. So how these particles are formed in flames? When they are very small, when they are molecular clusters, when they collide, they experience coalescence. So from a numerical point of view, we need to introduce a first critical diameter for coalescence. And after that, particle may agglomerate, or in some collision, they may experience some rebound. So we need to introduce a second critical diameter, that is the sticking critical diameter. That is not very clear in the literature, so we want to find this value. After this critical diameter, the particle, when they collide, they stick together after this point. At the same time, and in parallel, surface growth is increasing the size of the particle, and also is changing the chemical composition by dehydrogenation. So here an important result from the literature, they observed that when the particles with the size in this domain here, when they are quite small, when we increase the temperature, the agglomeration degrades. So they agglomerate in a slower way. That is not the case for mature soot or larger soot particles that agglomerate faster with larger temperature. So the question is why? In this study, when I say soot maturity, what I mean in this study, we mean an increase in carbon to hydrogen ratio and also an increase in soot bulk density. And we want to study the agglomeration kinetics and morphology effect that can be associated with this variation of maturity. And we also consider something that is typically neglected in the literature, the electric charges of these particles. So here how we consider the interaction between particles. So when they are agglomerates, the interaction is quite complex. So we decided to simplify a little the problem and consider just the interaction between the closest primary particle when two agglomerates, they come to contact. And there are three energies to be considered here. First of all, we have, here I show you the energy as a function of h is the distance between the surface of these closest primary particles. And here there are three energies to be introduced. First of all, we have the electrostatic barrier that is associated with the electrostatic charge of the particles. We have the potential well that is associated with the van der Waals interaction forces, and the kinetic energy that is associated with the particle mass and velocity. So here is the first case of interaction. When the kinetic energy is smaller than the barrier, the particle will repel each other, so they will not collide. Another possibility is that the particle arrive with larger kinetic energy than the barrier, so they will certainly collide, but there is rebound because there is too much energy compared to the energy necessary to have sticking. And that means that sticking needs a right amount of kinetic energy in collisions. So having this idea in mind, we have studied the collision of different agglomerates with different primary particle diameter. And also we have calculated the sticking probability with an expression we have introduced. And here I show you just the main idea. It is a function of the barrier, the potential weld, and the thermal energy. And here are the different cases we have studied. So mature soot, nascent soot, and variable maturity. And you can see they correspond to different carbon to hydrogen ratio and different mass volume fraction, but mass density of the particles. So here I show you the sticking probability as a function of the reduced primary particle radius. That is a function of their both radius of the interacting primary particle for electrostatically neutral particle. And you can see for mature soot, it is increasing with the reduced size. A similar case is shown when we consider soot to be nascent. And here is the first conclusion that the dependency of this probability on the chemical composition of the particle seems to be not so strong. And here in an intermediate case, when we consider the maturity to be variable with the size of the particle, and here an important remark, a small primary particle with a radius of 0.5 nanometer will hardly form an agglomerate. Why? Because the sticking probability will be at most 0.6, so most of the time this particle will rebound when they collide. On the other case, a larger particle with 12.5 nanometers, for example, they will most probably form an agglomerate because the sticking probability at the minimum can be 0.6. So most of the time, this particle will stick after collision. So here is our first result. We introduce a critical sticking diameter of 10 nanometers. What happened with electrostatic charges? Since we do not know the electrostatic charge of soot, we have taken some results coming from experiments in the literature, and we sampled in randomly from this Boltzmann distribution the charges of the interacting primary particles. And here I show you the collision probability for different charges of different primary particles. And you can see that for equally charged and large charge of primary particles, there is no agglomeration. And that explains why in the literature some people do unipolar charging of aerosol to avoid agglomeration. And the reason of that is just related with the energy barrier that increased a lot when they're equally charged. In other cases, the probability tends to 1 very fast. So we have implemented both the sticking and collision probability in our simulations. To this end, I have used the code we have developed that is called MCAC, Monte Carlo Aggregation Code. That is worth to say it is available in a GitLab repository, so you can use it if you want. In my simulation, I simulated a laminar premixed flame. I start with a 3.5 millisecond residence time with a distribution of primary particles that are considerably initially spherical with 2.5 nanometer in geometric mean and 1.2 geometric standard deviation. So the particle, in my simulation, I track the individual position of particle and I consider they agglomerate when they collide. So they will form this fractal-like structure and there is at the same time surface growth. So I consider different cases, as you can see here, one mature nascent. And when I say no potential, I am not considering the sticking or collision probability. When I say only LJ, I mean only Lennard-Jones. I am only considering the sticking probability. When I say plus electrostatic, I mean I am considering the collision probability also. So in more detail, how I do my simulation, from the particle dynamics point of view, the particles, they are considered to move ballistically along the persistent distance that depend on the diffusion coefficient and the momentum relaxation time. The friction coefficient depends on a power law of the number of primary particles. The sticking probability are calculated as you can see here. As I told you, it's an expression we have introduced in this work, and they are function of the barrier and the potential welds. From the surface growth point of view, we consider a molecular flux that comes to the surface of the particle and increase the size, as you can see in these equations over here. So here is the first result. We have calculated a monodisperse equivalent collision frequency, as you can see from this equation. Here I show you the evolution of the collision frequency as a function of the residence time. For the first case, the mature soot without any potential. After that, we added the sticking probability. So we see a small effect at the beginning of the simulation and also the end of the simulation. After we consider a nascent primary particle case, when considering the sticking probability, and we observe that the collision frequency increased for larger residence time. So we say, well, we have this result. So I conduct another simulation of also nascent soot, but without any potential weld. And the difference are mainly observed at the beginning of the simulation. And finally, we conclude that this variation is mainly due to the lower bulk density of nascent soot compared to other cases, and seems to be more important the variation of density than the sticking probabilities. And finally, the variable maturity case, where both sticking and collision probability are considered, they are very close to the mature case. Here I show you another result. When we express the inverse of the particle number concentration as a function of time, it is a power law with time, where the exponent is called the kinetic exponent. And we have observed before, this is a result we have observed before, that for when the agglomeration is ballistic, this value is larger. When the agglomeration is diffusion limited, this value is smaller, and much smaller even in the transition regime. So here are the results of the present work. So I express the inverse of the particle number concentration as a function of time, and I report the asymptotic kinetic exponent as you can see here. And once again, comparing maturity and variable maturity cases, they find similar kinetic exponent. And when we consider the variation of particle bulk density, very different kinetic exponents are found. And we observe here from this case that not considering the sticking probability will have a big effect for larger residence time, because the kinetic exponent seems to be very affected when we consider or not the sticking probability and the variation of bulk density. So here the particle size distribution, it seems not to be very affected when we compare mature case and variable maturity. I forgot to say it is expressed in terms of the radius of gyration, and it's sampled at the end of the simulation. And first of all, when we compare variable maturity and mature case, we observe that both the geometric standard deviation and the geometric mean value, they are not so different. But NAS and SOOT, it shows a larger geometric standard deviation, and that is related with the fact that the NAS and SOOT, they have less bulk density, so they collide more ballistic. So that's the reason they have larger geometric standard deviation. So finally, show you here the result of particle morphology in terms of the fractal law that you can see here. Where this is the volume of the aggregate, the volume of primary particle, the radius of gyration, radius of primary particle, and the fractal dimension and prefactor. So when we plot this in log-log and we obtain the slope here, we obtain the fractal dimension, and the log of the intercept is the fractal prefactor. So here are the result for the different cases I have studied. And what is the main conclusion is that the morphology seems to be not very affected by both the sticking probability and the variation of bulk density. So to conclude my presentation today, I have introduced a critical particle diameter for sticking to be 10 nanometers. I have observed that the effect of variable maturity is fast in this premixed flame and have a moderate impact on the agglomeration kinetics, particle size distribution, and morphology. But finally, what is an important conclusion of this work is that mass bulk density seems to have an important effect that should be considered for future works. So with this, I conclude my work, and I will be happy to answer your questions. So thank you very much.
Okay, hope you can hear me again. Thank you very much indeed, Jose. And congratulations on your poster prize at ETH. So we have at the moment we have one question in from Steve Rojak, who asks, in the collision dynamics for two aggregates, do you consider the redistribution of energy in deformation of the structure?
If I consider the, sorry, I didn't understand well the question.
In the collision dynamics for two aggregates, do you consider redistribution of energy in deformation of the structure?
Ah, okay. For my simulations, when two particles they collide, they agglomerate, and from that point of view, I do not interrogate what happened in the interaction between the particles. So when they collide, they form a rigid structure. And so I do not simulate the dynamics of each individual primary particle within the aggregate. So I do not consider the restructuring that might happen due to the interaction energy within the aggregate. I hope that answers the question.
Yes, I hope it does too. Any other questions about this? It feels like an awful long while since I've had anything to do with Leonard-Jones potential since I was an undergraduate. So it's quite nice to see actually that you can actually, and it's a very impressive piece of work to get that kind of agreement with the experimental results is very impressive. Any further questions?
I think there's a question in slide.
Oh, there is. Sorry, yes, there is. Yes, from an anonymous questioner. Oh, it's Adam. If a critical sticking diameter exists, would we expect to see many single small primary particles in TEM images? And is this found in TEM studies? Yeah, that's a very good question. In fact, yes. So I mentioned that a critical diameter should be around 10 nanometers according to our study. And from a TEM image numerical experimental point of view,
quite complex to say if they have observed lots of individual primary particles, because when sampling these small particles in the flame, it's quite complex. I understand. So I will say it needs to be checked. I would like to read more about it, but I am sure I have seen in the literature some TEM images where there are many individual primary particles. So, but it has to be checked if this particle they have the diameter is correctly lower than 10 nanometer and is coherent with what we observe experimentally.
Okay, thank you. Another question from Martin Irwin. Is it possible for the number concentration to overcome charge effects in soot production, i.e. forming agglomerates in an otherwise unexpected way?
It's possible for the number concentration to overcome charge effect in soot production.
Overcome, yes, I'm just... Martin, are you able to clarify that?
Yeah, can you hear me? Does this work?
Yeah.
Yeah, okay. So I mean, if you look at the model, you can, for example, say that you wouldn't expect formation if you look at a case-by-case basis, and that this data is really good and kind of clear. But my question is, if there's such a high number concentration in a soot formation, is it possible that overcomes like the sheer number of particles and collisions overcomes the theoretical, if you have two particles, their charge could repulse each other. If you have enough, could you form particles where you may not expect it due to the charging?
My question is yes, but from my simulations, I have not observed this effect, and I think it is related with the fact that the particle they are charged bipolarly, and also they have many neutral particles. So I have not observed this effect, but I have seen in the literature that, for example, when the particle they are charged unipolar or they are under a magnetic electric external electric field, for example, they can form different morphologies. For example, they can form very elongated particles, more compact, and that may have a big impact on the particle number concentration, because if you change the morphology, you will change the collision frequency of the particles. Because, for example, if you do more elongated particles, they may collide faster, so it will change the particle number concentration from a morphological point of view. So my answer is, in some cases, it might be very, very important, and it's not the case from this simulation I have done this time. But I may expect that for other flame conditions, other conditions where there is a larger volume fraction, for example, because here I think another reason I did not observe big impact is due to the small volume fraction. It is not a very sooty flame. And in other flame condition, I think it might be very much important.
Okay, thank you.
Okay. We've got a couple more questions in, and we've got a couple of minutes till the next talk needs to start. So Joel Colbin asks, does the predicted importance of density imply different shapes for silver versus soot aggregates? I don't think this has been observed.
Important density, different shapes.
Because I guess because silver is very heavy.
Yes, I understand. But for example, from a morphological point of view, we have not observed very big impact due to the change of particle bulk density. So from the particle bulk density point of view, there is no big impact on morphology. So I agree that from this point of view, we will not expect a big difference in morphology for soot particle and silver metallic particles that they have very different bulk density. So it's coherent with the simulation, I think.
Okay. Finally, very quickly, did you consider the fact that soot charge is bipolar and almost symmetrical?
Yes, exactly. In fact, I have, for example, here in the appendix, I have a comparison with the literature, And I told you before that I sampled randomly the charges from the Boltzmann distribution. So I assume that the electric charges, they arrive to an equilibrium with the ions naturally formed in the flame. And you say fast, sorry. So I assume they charge bipolarly, and this is quite symmetrical. And you can see here is comparable with experiment. And here I have another example, and for different mobility diameter, you can see it is quite symmetrical, and it's centered in 0 and depends, the standard deviation depends on the mobility diameter.
Okay, thank you very much indeed.